Jnanam paramam dhyayam. Knowledge is supreme.
So, last lecture we had seen how abstract vector spaces can be defined, and now we will look at the notion of perpendicularity and the inner product on abstract vector spaces. So, basically the idea is that the properties of the inner product, the dot product in R n are taken over as the definition of a inner product. So, given any vector space which is either real or complex, depending on whether reals or complex, for every pair of vectors u and v and w, we associate a number which is real in case it is over the reals, is a complex number if it is over the complex, and that number is denoted by that square bracket this corner bracket v w. So, it is a kind of a function, right, on v cross v to the underlying field. So, what are the properties of this? Basically that of inner product. So, it is linear in the first variable. So, if we have a linear combination lambda v plus mu w, inner product with x is same as lambda times inner product of v x plus mu times inner product of w x. So, in the first variable it is linear, right, scalars come out and addition becomes image of the addition is addition of the images. So, that is linearity in the first variable, and it says that if you interchange the two, so inner product of v and w is same as inner product of w and v if it is over the real numbers, right, if it is a real number. If not, then it will be a complex number. So, then it is the bar of that. Okay. So, inner product of v w. So, in general you can write it as v w bar, depending on real there is no conjugation. So, that will be same as this. And lastly, third property, namely that inner product of v with v is bigger than 0 and 0 only if and only if v is equal to 0. That is the dot product of a dot a is, right, in R n. So, that property. So, these three properties of the dot product are taken of R n and put as an abstract definition of a inner product on an abstract vector space. So, such a space we will call it as inner product space. So, it is a vector space either over real or complex, and for every pair of vectors there is a notion of a inner product or dot product, you can call it, with these three properties. Now, this property we said it is linear in the first variable, right. What about the second variable, right? So, because of this reason, say if you have something on the second variable coming out, say scalar multiple here, then it will be equal to lambda w v bar. So, that lambda in the first variable will come out as lambda bar, right. So, in the second variable it is conjugate linear if it is over complex, otherwise linear. Okay. So, consequence of the first property and the second property, that it is conjugate linear in the second variable. So, x lambda v plus mu w. So, addition remains addition, but the scalar from the second variable comes out as lambda bar and mu bar, right. So, that is because of this property 2. So, once we have this property v dot v is bigger than 0, we can define the notion of length, magnitude of a vector. So, magnitude of a vector is nothing but square root of the inner product of v with v, right. Norm a square is a dot a, right. So, same property holds here because of this. So, we define, so this gives us a definition of the magnitude of a vector in a inner product space, but to be equal to square root of inner product of v with v. So, basically the properties which were true for inner product in R n are taken as definitions in a inner product space, nothing more than that. Okay. We have Cauchy-Schwarz inequality for Rn, same property is true for any inner product space. So, we will not give a proof of this, we will assume it. So, inner product of BW absolute value is a real or a complex number, its absolute value is less than or equal to norm of, right, A dot B in the real line absolute value is less than or equal to norm A norm B, right, magnitude, same property is true. So, that is what we call as Cauchy-Schwarz inequality, and using Cauchy-Schwarz inequality one can prove the triangular inequality, that the length of u plus v plus w or v minus w is less than or equal to this, right. That proof is simple and straightforward, because if I look at the square of this left hand side, okay. So, I can write it as inner product of the same vector with itself, and now expand using your properties of the inner product. So, v and v will give you norm v square, w and w will give you norm w square, plus minus cross product terms, right. And now this is less than or equal to norm v plus norm v. So, put that property here, okay. So, it is less than or equal to, each one of them is less than norm v norm w, right. So, this is less than norm v norm w, this is less than norm v norm w. So, 2 times, and this is the square of that term, right. So, nothing more than that, using Cauchy-Schwarz inequality once, right, and using that v plus w square is dot product of it with itself, inner product, expand and use here Cauchy-Schwarz inequality, that each term here is less than or equal to this. So, that proves triangular inequality. Once you have the notion of dot product, we can define the notion of perpendicularity, right, in an abstract vector inner product space. So, 2 vectors are said to be orthogonal if their inner product is equal to 0, right. Once the perpendicularity is defined, you can prove the standard Pythagoras theorem, right. Norm of v plus w square is norm of v square plus w square if v and w are perpendicular to each other. And the proof is actually straightforward, you write this is norm square. So, expand it as dot product of this with itself, open it out, and because of perpendicularity the cross product terms will be 0, right. So, norm of v w and w v will be 0. So, you will get only this much. So, that is standard proof. And similarly, there is parallelogram law, which is again same, write this both of these as dot products, expand, and you will get the terms will cancel out and you will get the thing. So, proofs are straightforward. What you do? Write norm square as dot product of that vector with itself and expand, right. So, nothing more than that. So, Pythagoras theorem is true, parallelogram law is true for abstract inner product spaces once we had the notion of a perpendicularity, right. Same proofs work, nothing, no change comes. Okay. So, some examples, this is a prototype of inner product space in Rn, right. If we write V as a column vector, then V transpose W, this is a product of matrices. So, dot product is AI Bi, right. V is a vector with components V1, V2, Vn, W is a vector with components W, W, Wn. So, what is this Vj, Wj, right. This in between term is, if you want to write it as a in terms of matrices, if you write a vector in Rn as a column vector, then its transpose will be a row vector 1 cross n, 1 cross n, n cross 1 product will be a scalar, right. So, this is in terms of matrices, and for complex the only difference comes is you put a bar here. So, Vj, Wj bar, we had seen that in when we did. Now, let us look at an example of a inner product space which is different from all this, why this is required. So, that is this example. Look at the space of all continuous functions CAB. So, they are real valued continuous functions defined on an interval AB to R, right, and f is given to be continuous. So, all continuous real valued functions defined on the interval a b. You can add them, right. Any two functions can be added. F plus g defined at a point x is f x plus g x. Yeah. No, actually this is a typo here. This should have been star there actually. Yeah. So forget the middle term. Actually, there is a typo. This star should have been here actually in W. Okay. So that's why this is Wj bar coming there. Yeah, VW star. Okay. So okay, right. So on CAB, so let us just look at slightly more. Okay. So we have got CAB. So that is a space of all functions which are defined on AB to R, F continuous, right. So for two functions f and g belonging to CAB, if you recall, so this is a definition of the sum. So that is f x plus g x for every x belonging to AB, right. And what is alpha times f? So definition is alpha times f of x for every alpha belonging to R. So then CAB, under this addition and scalar multiplication, CAB is a vector space. It becomes a vector space because addition of functions is associative, commutative, right. Zero function is there. So all those properties hold. So it becomes a vector space. So this addition and scalar multiplication make it a vector space. Now on this vector space we are defining a inner product. So for two functions f and g belonging to CAB, continuous functions, look at the function f x, the product, right. Their integral from is over a to b dx. This integral is defined. If f is integrable, g is integrable, then calculus tells that f plus g also is integrable. So this number is defined, and this number we denote it as the inner product, right. So this is a definition of dot product for the vector space CAB. Want to check this has all the properties the dot product has, because if I write f plus g, right. So checking that this is a vector space. So let us look at f1 plus f2g. So what will be that? So that is integral of f1 plus f2x gx dx. So that by the properties of integration, right, the integration is a linear process. So this is nothing but a to b f1x gx plus a to b f2x gx dx, right. So we are using the property that integral of sum is equal to sum of the integrals, and that is equal to integral of f1 g. So that is the dot product of f2 of g, right. So linearity, and same way if you put a alpha here, so alpha f of g, so by definition it will be alpha f. Again property of integration, integration is a linear operation. So this alpha comes out, so that is a to b fx dx. So that is alpha, oh sorry, there is a g here, so gx dx and dx. So that is alpha times f of g, right. So that says that this is an inner product. We have not checked the other property. So what is the second property we had? F comma f should be greater than or equal to 0. So let us check that also. That is a straightforward again. So if I look at f comma f, that is equal to integral, f is same as g, so it is f square x dx a to b, right. Now f square is a non negative function, So, this will be always bigger than or equal to 0. Integral of a non negative function is non negative, and it is equal to 0. When is it equal to 0? When the function is identically 0, f square equal to 0. So, if and only if f is equal to 0, right. Integral of a continuous function, non negative continuous function is 0, if and only if the function is 0, right. So, f square is equal to 0, that means f is equal to 0, right. Okay. So, that property. So, that is the inner product. So, that is what we are saying, that this becomes a inner product space. F square equal to 0 means what? It is mod f square. Now, it is clear? Yes. F square, I can write it as mod f square. Is it okay? So, if mod f should be equal to 0, or mod f of sign that is not equal to 0. So, you will have a problem there. Okay. See, that calculus theorem is quite nice actually. If this is a and this is b, right, if the function is continuous and non negative, right. So, the graph will be above the x axis, right. So, that means what? Somewhere it starts non negative and non negative, and it has to, that is the graph of the function, right. So, if it is continuous function, then the area below the graph is equal to 0. If it is a continuous function and its integral is 0, that means what? If a function is non negative and you take its integral, right, then what is the integral? And it is the area below the graph of the function geometrically, right. If it is non negative, then it will be bigger than equal to 0. Okay. So, this, and if this area is 0, that means what? Our claim is, if this area is 0, function is non negative, then the function has to be 0 everywhere, right. So, let us see in the picture why is that happening. This is a to b. Suppose at some point c the function is 0, then what will happen? It is a continuous function, then what should happen? So, go back and look at your calculus thing. Okay. For a non negative function, if the integral is 0 and the function is continuous, that is important. See, if the function is not continuous, then you can give many kind of examples. For example, if the function is not continuous, I can give value 0 here and 0 here, and here I can give the value 1, right. Then what is the integral of this function? That is 0, right. Whatever the function may be, whatever the values is, value is 0 here, 0 here, and is 1. So, integral is 0, but the function is not 0 everywhere, because it is a discontinuity. For a continuous function, that cannot happen. Okay. So, this CAB, so what we are saying is, this space CAB with FG equal to integral f x gx dx a to b is an inner product right. Okay. You can just for the sake of a bit more understanding, this was a vector space, right, over the reals. So, and we have shown that it is infinite dimensional, right. This was the example of a vector space which is infinite dimensional. So, we got an infinite dimensional vector space on which a notion of inner product is also defined, right. So, keep that much in mind. Okay.